So good afternoon, everybody. A lot of my talks are looking out into the universe. This is one talk that looks inwards to the weird world of the very, very small. And what I'm going to be doing is trying to give you, to start with, a sense of scale, getting down to the very small scale from what we're used to, of an everyday scale, from meters, down to the world of nanometers, billionths of a meter. And I'll be looking at what the world is made of, looking to see how a sense of symmetry when we look at the macroscopic scale gives us some clues as to what's going on the microscopic scale, the underlying structure. And I'll finish with looking at how we can actually see the quantum world. In other words, how we can actually use the ideas of quantum mechanics to actually build a microscope that will allow us to see atoms. So let's start with something we're familiar with. We can see objects down to of order a millimeter or so. We're used to looking at objects on scales of meters or larger, but of course if we squint and if we've got the right set of specs, we can see objects down to a millimeter or less. And perhaps you're familiar with objects like this. If we look under a microscope with modest magnification, we can see objects at a scale of a fraction of a millimeter. Here we're looking at a pollen grain with a diameter of order tens of microns. Remember, a micron is 1/1000th of a millimeter, and we're going to end up at nanometers, which are a 1/1000th of a micron. So we can build things down to rather small scales. If we wish, we can build mechanical objects that are substantially smaller than a millimeter, if we so desire. But of course, the area where we've excelled in terms of building small components is in the field of electronics, because we can mass produce electronics such as the chippery that's inside the phone or the iPad or the computer that you're using at the moment. Typically, microprocessors have areas that are measured in square millimeters or perhaps even square centimeters. And there can be millions, perhaps that's a little bit out of date now, because it's not so much tens of millions of transistors. The latest chips might have 1 billion transistors on them. So the size of the individual components that we're talking about could be as small as 10 nanometers, and certainly in the range of 10 nanometers upwards is fairly typical of modern electronic technology. So we're already manufacturing things at the scale that are not much bigger than individual atoms. So what about the structure within? What is the world actually made of? And how can we tell what the world is made of? What clues do we have that tell us what matter comprises? Well, if we go back a little way, Aristotle told us that everything is made of earth, air, fire and water. A very simple periodic table, and unfortunately a little too simplistic to explain all of the things that we see around us. But then along came Galileo, in which the nature of the world around us, he posited, should be determined by quantitative experiment, not by qualitative intellectual arguments. In other words, Galileo was one of the first people to come along and say, you shouldn't ask, for instance, what should happen if I cut this material in half, or what should happen if I drop this object and let gravity do its stuff. You shouldn't ask what you think ought to happen. You should actually do an experiment and find out what actually happens. So in a sense, Galileo was the first experimental physicist who said, rather than come up with simple intellectual arguments, you should find out the actual answer. Newton refined this and of course came up with lots of science, lots of elements of laws of physics that we now understand, such as his laws of motion, law of universal gravity, the nature of light, etc. And if you take all of Newton's understanding of the physical world, you can put that all together and talk about so-called classical mechanics, or sometimes Newtonian mechanics. But we now realise that if we want to delve into the very, very smallest elements of matter, we have to go beyond Newton. So Newton believed that basically the universe was clockwork. The universe is put together in a particular way. We don't necessarily discuss who made the universe, but the universe seems to exist and it seems to operate. And in other words, if you look at the way the planets go round the sun, if we understand where the planets are and the way the planets move, then we can basically say where they used to be and where they will be in the future. If everything is clockwork, then we can say precisely how it works in the sense of where things are, how things move, where they will be in the future. We can predict precisely, as long as we understand at the moment the current state of a particular system, we can predict how that system is going to change in the future. But when we look at the state of matter, for instance, when we look at snowflakes, we see they're all different, but they all have apparently a six-fold structure, a six-fold rotational symmetry. Surely that must tell us something about the way the world is made. Newton might be able to tell us how objects move, and if we apply a force to an object, that object will then move in a particular way. But if we want to understand why does a snowflake look like that? Why are they all in this particular pattern of six-fold symmetry, even though they all look different? Then we know that that is telling us something. There is no way that the building blocks of a snowflake can produce lots of six-fold snowflakes without that telling us something about the way those building blocks are linked together, the way they are constructing matter. And when we look at not necessarily ice, when we look at certain metals, again we find clues, because certain metals crystallize in particular ways, and the particular angles and shapes that we can see in this crystal, this particular crystal of bismuth, that must be telling us something about the way the building blocks, whatever they are bolted together. And similarly with naturally occurring minerals, and in some cases rather bizarre materials which seem to crystallize in shapes that we are not generally familiar with. We're used to the idea of crystals crystallizing into either hexagons or perhaps into squares or rectangles, such as we see on the left-hand side. But more recently we found crystals that produce these rather unusual shapes, these dodecahedrons. These five-fold faces, these pentagons, must be telling us something about the way the building blocks are put together in order to create macroscopic crystals that we can see with our eyes. The macroscopic structure must be telling us something about the microscopic structure, the structure of whatever lies underneath the surface. So that's effectively how we started to get a handle on what must the world be made of. We can say intellectually, well, maybe it's made of building blocks, but how do we actually know that, and how do we find out about those building blocks? Well, it's been a long story since Democritus first came up with the idea of maybe if you took a material and cut it in half and then half again and then half again, maybe you can't do that indefinitely. Maybe you will come down to something which is indivisible. And that's where the name atom originally came from, the indivisible building block of all matter. But our understanding of what atoms are has progressed over many, many decades. I'm starting here from 1600 to 1900, and then I'll look in a little more detail in just a moment at 1900 onwards. I'm not going to go through all the contributions of these people in terms of what they did, but perhaps you may or may not recognise some of the faces that I've got here. So we start with Boyle, and then perhaps you recognise Newton. Then we have Lavoisier, and then Dalton, and then Avogadro, and then Maxwell, and then Boltzmann. So they are placed, roughly speaking, where they belong in the timeline. Virtually all scientists will have made contributions over many years, perhaps many decades, and so this is just a rough indication of where these individual players came into the timeline of developing ideas about atoms. A lot of this, during the centuries I've indicated here, a lot of this came from our understanding of chemistry, looking at chemical reactions and finding that this material reacts with this material and produces this result, and that gives us an idea of what those building blocks must be in order to explain the particular results of chemical reactions. But in the 1800s, two people in particular gave us insight into what the world looks like on the scale of the very, very small. In the early 1800s, we've got Young, who performed an experiment by shining light through slits and showed that the light interferes in much the same way that we see interference of waves on the ocean, for instance. So Young determined that light, and it doesn't really matter whether we're talking about visible light or other wavelengths of light, so let's just talk about visible light here. Young was the first to show that light behaves like a wave, so light is made of waves. And in the later part of the 1800s, along came J.J. Thomson, who showed us that electrons are particles, and electrons are presumably parts of these building blocks. They can't be the only building blocks of matter, because electrons have a negative charge. And so it was postulated there must be other particles with positive charge to give the overall neutrality that we see in matter. Otherwise, every particle of matter would repel every other particle of matter if they were only made of negatively charged particles. So in the 1800s, we seem to have a relatively nice result. Light is one thing, it's got a wave nature, and particles and electrons are one example of those particles. We have yet more to find, but electrons are objects, billiard balls if you like, small particles and presumably indivisible. But they are not atoms because we must have other particles involved. But when we move from the 1800s to the 1900s, well, all hell lets loose basically, because we have another load of players. Notice that the timeline here is only 30 years. This was a very busy period for trying to understand the world of the very, very small. And again, lots of people made lots of contributions. I've indicated their photograph here just as a point of illustration. Their contributions spanned probably many decades. Again, let's just remind us who these key players are. Becquerel, Planck, Rutherford, you presumably recognise Einstein in the centre then, and then we have Bohr, and we have de Broglie, and we have Heisenberg and Schrödinger at the end there. I'll try and give an indication of the main results that came out of these early decades. I am not indicating that each result can be pinned onto one person, but I just want to show you that a lot of discoveries were made in these early decades of the 1900s. Radioactivity was discovered and explained. It was determined that light is made of particles. The existence of atoms was established along with the positively charged atomic nucleus. It was realised that probability is key to understanding the very, very small, and it was determined that electrons actually have a wave nature. The QM on the right-hand side simply is shorthand for Heisenberg and Schrödinger were the architects of what we now call quantum mechanics, the explanation of what's going on the very smallest of scales. So the previous century, it was determined that light was a wave and an electron is a particle. But now look at what we've got. Those have both been turned on their heads, because now it's been determined that light behaves like a particle and electrons behave like waves. And you can see why things were very, very confusing. And indeed, it is still confusing. And when you try and teach this subject, you still have to be careful of how you teach, because ultimately you can't simply say light is a wave or light is a particle. And similarly, you can't even say that an electron is a particle or an electron is a wave. You have to accept that in the world of the very, very small, these distinctions get blurred. And when you start thinking about what do we mean by a particle or a wave, you have to realise that our descriptions are not always adequate to explain what these things actually are. So, in a sense, Heisenberg and Schrödinger took all of the results they had seen in the previous few decades and everything that was built from previous centuries and tried to construct a theory in which a mathematical model of how the world works explains effectively what atoms are and how particles and waves behave on the smallest of scales. But you can see that it's not a simple story. There are dozens of individual players, of whom I've indicated some here. Lots of people making a contribution, lots of people trying to understand, sometimes rather conflicting evidence as to how we should explain how the world works on a small scale. So this is quite a common picture, that an atom has got some building blocks of its own. In other words, although you can't cut an atom in half and have simply half an atom is made up of other stuff. There's positively charged particles in the middle and negatively charged particles, if you like, orbiting around, as in this particular picture. This, if you like, is a representation of one particular type of atom. It's an atom of the element that we call boron. It has 5 positive charges in the centre and 5 negatively charged electrons buzzing around it, like bees in a beehive. So that's one way we can think of an atom, and that's a very popular way of thinking of an atom. But it's not particularly helpful in the sense that in this particular picture all the electrons look the same. In other words, they all behave the same and they all would look the same. If you took that picture and looked at it from any angle, all of the electrons would seem to be behaving the same way. But in fact, when we look at atoms and probe their properties, which we can do by looking at the way atoms interact with light, we realise that each of the electrons in an atom could have a different energy, which doesn't get reflected in that particular picture. So we need a different model of the atom to reflect the fact that all the electrons are different, or all the electrons might be different. And part of what was happening in those early decades of the 1900s was trying to refine the idea, if you like, trying to refine the picture of what an atom must be to make it consistent with all the observations that were coming out at the time. So rather than that picture of an atom, perhaps it would be better to think of the electrons as being different distances from the nucleus. If there's a positively charged nucleus, we can think of an electron, as it were, orbiting a little bit like a planet orbits the sun, but different electrons would be at different distances from the nucleus. So the picture at the top is a sort of pancake view. It's a two-dimensional representation of different electrons, lots of them in this particular case, all buzzing around the central red nucleus. But although that's a two-dimensional representation, we have to remember that actually an atom is a three-dimensional object. So a slightly better way of thinking of it, rather than think of it as rings or orbits around there, we should think of it as shells, and we've cut these shells in half at the bottom there to remind us that electrons are actually moving around the nucleus in 3 dimensions, but there are still shells of different electrons that have different energy, simply because they are different distances from the nucleus. So that's a slightly better way of thinking about what's going on inside an atom. And if we take that particular model, then we can start to make sense of the world around us, because we can then understand why we have different elements. Hydrogen has a single proton and a single electron. Other elements will have lots of protons and lots of electrons around them. And each of the elements in the periodic table has a particular unique arrangement of positively charged particles in the nucleus and negatively charged particles buzzing around them. So as soon as we start to understand the nature of atoms, we can start to understand why we have 92 elements in the periodic table, and we can start to understand chemistry based on, we now think we understand why this element reacts with that element, because it involves how the electrons are behaving in these two systems. So chemistry and physics overlap in the sense of the physics understands the arrangement of atoms, and that then explains why we have chemical reactions the way they occur in nature. So is it fair to say an atom is a bit like a solar system, a positively charged nucleus surrounded by electrons? Is that the same as a big sun in the middle of a solar system surrounded by the planets? Well, we've already said that the solar system looks a little bit two-dimensional, whereas atoms are three-dimensional. And it's also not a very good model for other reasons. So we could say, well, is it better to think of the electrons as being like satellites going around the Earth? If you think of the GPS satellites buzzing around the Earth, there are lots of them, they're all buzzing in different directions. Okay, they're all at the same height, so it doesn't give us a picture of all the electrons being of a different energy. But is that a better way of thinking about how an atom is actually put together? Well, the main problem with any of these pictures is that they are all clockwork. in the sense that if we look on a macroscopic scale at a satellite going around the Earth, if we know where the satellite is now, we can predict where the satellite is going to be in the future. But when it comes to looking at atoms, it was determined in the early 1900s that a key element of how the world works on the smallest of scales is that all we can talk about is the probability of something happening, the probability of an electron being in a particular place at a particular time, for instance. So if we've got a nucleus and an electron, on the atomic scale we cannot say this electron is here and in a fraction of a second's time the electron is going to be there and then the electron is going to be there. We can do that for satellites going around the Earth, we can do that for planets going around the Sun. But when it comes to explaining subatomic particles, the best we can do is to say what's the likelihood, what's the probability of this electron being in this location. And that gives us these rather fuzzy looking pictures of what an atom might look like. These fuzzy looking clouds are indicating where an electron is likely to be relative to the nucleus. In other words, if the nucleus is where my cursor is, these little clouds here tell us where an electron is likely to be, where the brighter part of the cloud is telling us where it's most likely to be, and the darker parts of the cloud are telling us where it's less likely to be. And each of these 8 rather odd looking clouds is a different electron in an atom. So you can see that this picture of a solar system isn't really right. It's not a nicely well-ordered solar system in which we can track and predict where all the electrons are going to be. It's a much more messier system where the best that we can hope for is to predict probabilities of things happening. Probability of position, or probability of speed, or probability of energy. So here we have the problem. When we're dealing with atoms, how should we deal with these mysterious things called atoms? Should we describe an atom using words? Should we use words in English like waves and particles and electrons orbiting a nucleus? And should we talk about an electron spinning? And should we talk about energy? The main problem with that is that each of these words has a particular meaning independent of talking about atoms. In other words, each of these words already existed in the English language before we came along and started to try and describe atoms. So in other words, each of these words has a little bit of baggage associated with it. Because if we start saying, well, the electron has a property called spin, then in our heads we say, well, spin, that means something is turning on its axis, rotating as it were, which is not, strictly speaking, what's going on with an electron. So the words we use, we have to be very careful because the words don't necessarily mean what at first sight we think they mean. So words are not a very good way of describing what an atom actually is. Okay, so let's not use words. What about using pictures? Now that splash screen isn't a very good picture of an atom, but maybe these clouds are. These clouds represent where an electron is likely to be in an atom. Well, okay, but they're still just a representation. We know that we shouldn't be thinking of an atom as a little solar system, and maybe these clouds are the best we can do in terms of trying to picture what an atom would look like. But the bottom line is, no natural language like English is capable of describing the behaviour of an atom. Pictures sometimes help us, but are strictly not the correct way of describing an atom. And the only language that is capable of describing what an atom does is not a natural language like English, it's an invented language which we call mathematics. So it is possible to describe the properties of what's going on at the atomic level using maths. And that is the second big problem, is people don't like maths. And if you want to teach a student how things work, quantum physics, you have to deal with the maths. And along the way, of course, it's not just maths. If you want to teach somebody the maths of quantum mechanics, you always use pictures to try and help. And you always try and explain what you're doing using words. But you always have to come back to the maths gives us the right answer, and to explain what's going on we have to try and find the right English words, and sometimes we try and find a picture which helps us understand what the maths is telling us. So I'm not going to be going into the maths, you'll be delighted to know. If you want to teach a student how to actually apply quantum mechanics to an atomic system or to a molecule or to the principle anything, you have to go through the basics of the mathematics and build up to the sort of thing we're looking on the screen there. And at first sight it looks like gobbledygook, because you have to understand what this maths is telling you before you can apply it and then start to say, well, this answer gives us this mathematical result, what does that actually mean? And there lies the rub. Heisenberg, one of the architects of quantum mechanics, has said, we wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. In other words, if we use ordinary language, the words don't necessarily mean what we think they mean, or at least when we're trying to discuss it with somebody else, we have to be very careful with the words that we use. So shouldn't we use different words then if the words get in the way? If words have baggage, if they have preconceptions, or if they come with connotations that we don't want to use, rather than say, well, when I want to describe this this electron in this atom, instead of saying the electron's orbit and the electron's spin, maybe I should say something different. Maybe I should say the slithy toes did gyre and gimble in the wave. Because you could argue that those two sentences in red carry exactly the same amount of information. As long as you say, what do you mean by electron, what do you mean by orbit, what do you mean by spin, and what do you mean by atom? In other words, each of those is just a label given to a concept, and it doesn't matter whether the label is electron or whether the label is tove. And it doesn't matter whether you're talking about atoms or wave, or whether you're talking about gyring and gimbling, or whether you're talking about orbiting and spinning. As long as you define what you mean, in principle they contain the same information. But when we talk about electrons orbiting, our head says, you mean orbiting, like the Earth orbits the Sun. No, that's not really what it means, but unfortunately that's what comes to mind when you use that word. And that's the problem with quantum mechanics, is when you're discussing things you have to be very careful with words. Here's Niels Bohr. Everything we call real is made of things that cannot be regarded as real. That is a pretty amazing statement. We believe that we are made of solid stuff. We believe that everything around us is made of real stuff. Of course it's real. And yet, when we break it down to atoms, atoms seem to be rather ghostly, ethereal things that have no solid existence. They are simply objects that appear to obey a certain set of mathematical rules, mathematical laws, if you like. And there's the quandary that existed in the early 1900s. How can we put together a theory of what the world is made of if it appears to be made of atoms which behave in such a weird way that we can't regard them as being solid objects in the same way that we can regard the macroscopic world as being made of solid objects? Atomic physics has shown that atoms have no meaning, but can only be understood in experimental measurement. Again, a rather amazing statement for the person that basically came up with the idea of quantum mechanics. Atoms have no meaning. They are simply useful ways of explaining why the world works the way it does. In other words, if we want to understand that we are made of cells, and the cells are made of molecules, and the molecules are made of something else, well, we can drill down to the fact that fundamentally everything is made of atoms. But when it comes to the atoms themselves, we can explain the behavior of those atoms in terms of mathematics and essentially nothing else. We can say that if we were to do an experiment, if we wanted to understand the way DNA behaves, we can do that by using the laws, the mathematics of quantum mechanics to tell us this is the way it behaves, this is what will happen if. if you smash two atoms together, this is what's going to result. But we can't really define that atoms have meaning. They are just useful ways of explaining how we end up with the world that we're living in. I don't like it, and I'm sorry I ever had anything to do with it. Again, this is the architect of quantum mechanics who says he's not altogether happy with what he's built. He built the idea of quantum mechanics explaining the way the world works, but even he wasn't happy with the results because he didn't like the fact that everything was producing results that were based on, for instance, purely the probability of something happen. There was nothing definite, there was nothing clockwork in there. And quantum mechanics often goes at odds with common sense. This is where people have a problem. So, for instance, the idea that atoms behave according to a set of rules that talk about probabilities, well, if you say it like that, that doesn't sound too bad. But it means basically you can't say anything with any degree of certainty. Any particle, the behavior of any particle, is unpredictable. So you can know the probability of something happening, you can know the probability of an atom having a particular position, having a particular speed, having a particular energy, interacting with another atom in a particular way. You can know the likelihood of the result, but you can never predict what's going to happen. And some people really, really, really do not like the idea that we can only talk about probability, not talk about what is going to happen if. And I mentioned that the world apparently is made of atoms, so presumably atoms are very small. But if you think about an atom being a nucleus and an electron, well, how far away is the electron from the nucleus? Well, we can't say. Remember, we can only talk about the likelihood, the probability of an electron being a particular position. So we can say, in a given atom, how likely is it that the electron is a given distance from the nucleus? And we can find an answer for that. And we can ask, how likely is it that it's this distance away? And we can find an answer. And we can ask, how likely is it that the electron is a long distance away from the nucleus? And we can calculate that and we can get a number. And we can do that independent of how far away we take the electron from the nucleus. It doesn't have to be just a fraction of a nanometer away. We can ask, what is the probability that the electron is a micron away or a millimeter away? What's the probability that the electron is 1 meter away from the nucleus? We can calculate that. What's the probability that the electron is 10 meters away? A kilometer? 1,000 kilometers? What's the probability that this electron distance to the nucleus is actually a couple of light years? Quantum mechanics allows us to calculate these numbers. So the bottom line is, an atom doesn't have a size in the sense there is no limit, there's no sphere we can put around the nucleus and say the atom is quite definitely inside this sphere, because the electron could in principle have a distance to the nucleus which is very large. We can talk about probabilities, we can't talk about absolutes. So you could say an electron could be anywhere. It's unlikely to be anywhere, it's most likely to be right next door to the nucleus, right next to the nucleus, and so only a tiny fraction of a micron, only a few nanometers or a fraction of a nanometer away from the nucleus. But it might not be. So we can't, strictly speaking, say that the atom is small. All we can say is the electron is probably fairly close to the nucleus. So the likelihood is that most of the electrons would be found fairly close to the nucleus, but we can't talk about absolutes. And again, this causes some people problems. Not only can we only talk about probabilities, we can't even state things that seem obvious. If we talk about an object spinning, like the Earth, as seen from the North Pole, the Earth is spinning anti-clockwise. But if we imagine a small particle like an electron or even an atom, we could in principle be talking about the object spinning clockwise and anti-clockwise at the same time, which makes no sense whatsoever. Quantum mechanics allows it. You could argue that quantum mechanics requires it in order to work, but common sense well, that throws a wobbly, because we say, well, how on earth can that be true? How can the electron be here and there at the same time? How can it be spinning clockwise and anti-clockwise at the same time? How can it have this much energy and this much energy at the same time? Quantum mechanics is a theory which allows that, but common sense gets in the way, because common sense tells us, bizarre, no, it can't be right. But Einstein made a useful quote: common sense is a collection of prejudices acquired during your childhood. In other words, common sense and quantum mechanics, there is no reason whatsoever why they should agree. Because you spent 18 years as a child coming into adulthood trying to make sense of the world. And at no point did quantum mechanics manifest itself as something you needed to worry about. You were simply trying to work out why it is that if you fall over you graze your knee, or where's the next meal coming from, or is this dangerous, or why is the sky blue? You're trying to answer questions based on common sense of trying to build a world model. But when it comes to quantum mechanics, everything you've learnt in terms of common sense doesn't necessarily apply. And it's a common sort of mantra amongst physicists: if quantum mechanics disagrees with common sense, it's because common sense is wrong and quantum mechanics is right. And the only reason that sounds odd is because you've spent 18 years building up a model of common sense. And then when you decide that you want to learn about quantum mechanics, unfortunately, you have to throw away a lot of what you thought you knew about how the world works. This idea of you can only talk about probability. You toss a coin, you cannot tell in the quantum mechanical sense whether you're going to get heads or tails. Now, you know that when you toss a coin you don't normally know. That's just because it's difficult to keep track of how many revolutions the coin has taken in the air. But in quantum mechanics it is fundamental that if there are two possible outcomes of something, you cannot predict which of those two outcomes will occur. You can only talk about the probability of those two outcomes. Einstein never liked this idea. God does not play dice, he says. God is subtle, but he is not malicious. Einstein tried to square the circle and come up with a theory which does not involve God playing dice. Other people said that's not the correct angle. In other words, the universe is fundamentally probabilistic, not clockwork. So rather than Einstein saying God does not play dice, other people came in with, stop telling God what to do. This is the way the universe is. Get used to it. Some people accept that, some people don't accept that. Let me talk about three aspects of quantum mechanics. Firstly, the fact that the order of things matters. Then I'll mention Schrödinger's cat, and I'll finish with how quantum mechanics can allow us to see atoms. So first, order matters. Now in algebra, we know that A times B is the same as B times A. 2 times 3 is the same as 3 times 2. The answer is 6, regardless of which order you put the A and the B. But in quantum mechanics, it does matter how you do things. So what? Well, let me just show you how bizarre that is if we do a little experiment and pretend that animals will behave according to quantum mechanical rules. In other words, if animals behaved according to the rules of fundamental particles, what would be the consequences? Let's take 4 animals. The top pair are carnivores, the bottom pair are vegetarians. So we've got a lion and a vulture, carnivores. We've got a waterbuck and an ostrich, which are vegetarians. But we could take these 4 animals and catalogue them differently. We could say the left-hand pair of animals have got 4 legs, the lion and the waterbuck, and the right-hand pair of animals have got wings, the vulture and the ostrich. Yes, I know the ostrich can't fly, but it still has wings. If we were to take these 4 animals and do the following, pick out 2 of the 4 animals. Let's say, for the sake of argument, we're going to pick out the vegetarians. Okay, we pick out the vegetarians and we're left with the waterbuck and the ostrich. Now, from those that we've just selected, let's pick again. Now, let's pick out the 4-legged animals. Now we would expect, of course, to be left with the water buck. But if we're doing this experiment at the atomic level, at the fundamental particle level, we would not get the water buck, we would get the lion and the water buck. In other words, even though we dismissed the lion as not being vegetarian, when we made the second choice, the lion comes back again. This doesn't happen in common sense, but it does happen in quantum mechanics. And if we do the same thing but now in a different order, what if we take the four-legged animals, so we've got the lion and the water buck, having chosen those two, let's choose again, and from that pair, let's choose the vegetarians. We would expect to be left with the water buck. But no, we're left with the water buck and the ostrich. In other words, the choice of the second pick seems to forget the fact that we originally picked the four-legged animals. This doesn't make sense when you're picking socks out of a drawer or picking animals from a zoo, but this is the way things work when you're dealing with quantum mechanics at the atomic level. Disagrees with common sense, but that's the way it is. With Schrödinger's cat, perhaps you've heard of this. It's a thought experiment. No, physicists aren't this cruel. It's a thought experiment in which you put a cat in a box and you have a 50-50 chance of the cat dying. Doesn't matter how. You close the box and then there's a 50-50 chance the cat dies. But if you don't open the box, the question is, what's the state of the cat? And just like we said earlier that an electron can spin clockwise and anti-clockwise at the same time, that's the odd situation about Schrödinger's cat. If we've determined that there's a 50-50 chance of the cat being alive or being dead, then before we open the box to actually see what's happened, it's not a question that the cat is one or the other and we don't yet know what the answer is. According to quantum mechanics, the cat is dead and alive at the same time, and until we open the box, only then does the cat become a live cat or become a dead cat. Up to that point, it is both at the same time. And again, this makes no sense in terms of common sense. You might just about believe it can happen for a fundamental particle, that it might be able to spin both ways. I can't work out what that looks like, but you might believe that a particle can spin both ways at the same time. But how can you possibly believe that a cat can be dead and alive at the same time? This is simply a thought experiment which brings to light the fact that although quantum mechanics seems to be a very good theory at the atomic level, if we take it above that to the macroscopic level, then we start getting some very odd, very weird results which we have to try and think, what does that actually mean? So I've said some of the weird things about quantum mechanics, but why do we believe it? Why don't we just throw quantum mechanics away and try something else? Well, the basic line is, so far, although quantum mechanics has existed for a century, nothing has proved it wrong. We know certain things happen in atoms and molecules and small-scale structures that Newtonian mechanics, the mechanics of Newton, cannot explain. And so far, quantum mechanics has given all the right answers. When we apply quantum mechanics to small-scale things, although it seems to give bizarre predictions, those predictions have always proven to be correct. We've never yet shown that quantum mechanics is wrong. That doesn't mean it's right, it just means we haven't yet been able to prove it wrong. Quantum mechanics predicts things that are essentially impossible according to Newtonian classical mechanics. So that's why we believe quantum mechanics is probably right. And using quantum mechanics, we can actually use the principles of quantum mechanics to build ourselves a microscope that allows us to see atoms. Such a microscope is called a scanning tunneling microscope, or an STM for short. What involves is we've got a tip, a metal tip. This is just showing the last few atoms of the tip that's brought close to a sample, and again the sample is represented just by a few atoms here. We connect the two together and put a voltage between them and measure how much current flows. If the two are not touching, then it's an open circuit and no current flows, according to classical mechanics. But according to quantum mechanics, a current will flow because electrons will appear in the gap between the tip and the sample, where according to classical mechanics they should not be. According to classical mechanics, it's impossible for an electron to exist in between those two metal objects, the sharp tip and the sample. So quantum mechanics says a current will flow, classical mechanics says a current will not flow. So we can do this experiment, we can take this, this tip, this red pyramid if you like, and we can move it across, in this case, a rather rough surface. If we move the tip across the sample and measure how much current flows, the amount of current that flows depends on, critically, on this distance between the tip and the sample. And you can see here the distances change depending on where the atoms are in this particular surface. And it is sensitive enough to measure differences even though these distances change by only a fraction of an atom. The distance between the tip and the sample, if it changes by a fraction of an atom, it produces a change in current which is large enough to measure relatively easily. So by moving the tip and measuring the current, we can effectively map out what the surface of a material looks like. And we use a scanning tunneling microscope, which is in the object behind me there. So inside this stainless steel ultra-high vacuum vessel, in which the air has been pumped out so as not to interfere with the experiment, a tip has been moved over a sample, and that gives us a picture like this. Each of these tiny little mountains here are individual atoms. Look at the scale in the bottom left there. We can see that a number of these peaks fit into 2 nanometers. So we're definitely looking at the atomic scale here. Not only that, but we can tell how these atoms are arranged in space, and we can see that they're not arranged uniformly over the entire sample. There are these apparent islands in which there are maybe a dozen or more individual atoms, and other regions, this sort of sea between the islands, which looks a lot smoother. So we can study surfaces and look at where the atoms are and how the atoms behave, and we can see those atoms because we are using the quantum mechanical effect that works in these so-called STMs, these scanning tunneling microscopes. And when we look at lots of materials, we find interesting patterns. For instance, here the bright areas are high objects, in other words, probably individual atoms, and the darker areas are the regions in between atoms. And so by looking at the patterns of light and dark, we can see how atoms are arranged. Notice that some of these arrangements appear to be high dots, high atoms, arranged in pentagons. So if that's how atoms are arranged, that explains why the crystals of this material on a macroscopic scale of millimeters or centimeters appear to have this dodecagon type structure, because the individual atoms are arranged in pentagons when we look at them at the nanometer scale. Just like if you were to look at ice, the hexagonal arrangement of the atoms and molecules in ice explain why snowflakes have 6-fold patterns. Here, the 5-fold arrangement of atoms in the crystal explains why the crystals look the way they do on the largest of scales. And by looking at individual atoms, if we measure distances between atoms, we find some interesting results. If we look at the ratios of the distance of these atoms to those atoms, we find, for this particular material, a particular ratio keeps cropping up, 1.6 and a bit. This is the same ratio as if we took a pineapple and counted the scales in one direction and counted the scales in the other direction. The ratio of those two numbers is 1.6 and a bit. And similarly, if we took a sunflower seed head and counted the seed head numbers going in one spiral pattern and then going in the other spiral pattern in the other way, we find if we take those two numbers, divide one by the other, we get 1.6 and a bit. So there are certain patterns in nature that exist both at the atomic level, dictated by quantum mechanics, and also at the macroscopic level. And that's an intriguing set of patterns that seem to transcend different spatial scales. And people are studying systems to try and understand exactly why that should be. I'll leave with an interesting image here, a a scanning tunneling microscope image of a corral, a large circle of atoms. You can see there are quite a few dozen atoms here. Each atom is showing up as a little mountain, apparently in a big circular mountain range. So here we seem to be indicating that individual atoms are behaving like particles, because each of them appears to be a bump in this particular image of the surface. But what's going on inside this corral of atoms? We don't seem to be getting a collection of points. We seem to be getting what looks like ripples on water. What happens if you throw a stone into a pond? You get ripples that look a little bit like what's going on in here. So this single image appears to indicate that some atoms behave like particles and some atoms seem to behave like waves. Again, coming back to the confusion of how should we choose the words or the description of what an atom or a particle actually is, when sometimes they seem to behave like what we understand as particles, as small snooker balls, but sometimes they seem to behave completely differently, as if they were waves. A single image capturing elements of both, which again sort of summarizes the fact that we have this conundrum of whether we should be describing them as particles or waves. Bohr came up with this: if quantum mechanics hasn't profoundly shocked you, you haven't understood it. In other words, if you think that quantum mechanics is just a, yeah, that sounds fine, I can deal with that, then you haven't grasped the fact that quantum mechanics gives some really bizarre, really weird, really nonsensical predictions. And we have to come to our peace with it and either decide quantum mechanics is right and we're going to have to get used to weird, or if we don't like weird, we're going to have to come up with something that replaces quantum mechanics as an explanation for how the world works on the scale of the very, very small. The best quote of the day probably is from Einstein. The most incomprehensible thing about the world is that it's comprehensible. We seem to live in an expanding universe, which is incredible. We seem to live in a world in which the behaviour of objects that are rather tinier than us behave according to rules that don't seem to agree with common sense. But the most amazing thing is that we can make some sense of it. Quantum mechanics for 100 years has given us a way to understand the world of the very, very small. The fact that we might not like it is neither here nor there. We can at least comprehend that quantum mechanics gives us the right predictions. So the fact that we can make any sense of the world is pretty amazing. For the monkey brains that we are. We were swinging in the trees of the savannah 500,000 years ago, but now we've got to the point where we can understand the universe and we can understand atoms. Not a picture I've taken, but I love this picture. It's an image of individual atoms. Note the scale, less than 1 nanometer, less than 1 billionth of a meter on each side, 850 picometers. So we're looking at a handful of carbon atoms there, imaged with a scanning tunneling microscope. If you were to imagine that's what individual atoms are, how big would a grain of sand be on the same scale that we're looking at? Well, a sand grain would be about the size of the moon if we were looking at it with this magnification. Which is why I always tend to think about the quote from William Blake: to see a world in a grain of sand and a heaven in a wild flower. Hold infinity in the palm of your hand and eternity in an hour. Thank you for listening.